So next we have the presentation of the best student paper, or best paper with a student lead author, I think is the title. Authors. Presented by Alon, and yeah,
Okay.
thanks.
Okay. Can you hear me? Okay. Thank you for the nice introduction, Nicole. I'm going to talk about interdependent values. It's a joint work with my advisors, Michal, Feldman, and Amos, Fiat from Tel Aviv, and with Kira Goldner, the other student, and Anna Karlin from UW. And I'm going to start off with a question. How much would you pay for this picture? This is a dog doodle for those who can't see it. So $1, anybody? $5? $100? Okay. $10,000? Okay. So how about if I give you the following piece of information? Okay. This is a Picasso painting. It really is. And this comes to show that something in the interdependent values model, that your value depends on the information you might not have. And even worse, this information might be in the hand of another player, another agent. And so in this example, for instance, your value changed after you saw the signature. Another example you can think about is maybe somebody is selling a house, and there are several potential buyers come and each has a private inspection. So somebody notices the parking situation, somebody sees the rats, another one might see there are a lot of playgrounds around, another one might see that the gardening is in bad situation. So each one has a private inspection, but its value depends on all the private inspections. So somebody, even though somebody didn't notice that the house has rats, he might care about this information. And this is captured in the interdependent values model by Milgram and Weber. In this model, we have one buyer and n potential buyers, one seller and n potential buyers. Each one has a private signal, a private inspection in the last example. For instance, the gardening situation or the rats. And you can think about it as a real number. So the signal is private, but the valuation function that he has depends on all the information, on all the inspections of all the players. And this is public. This is known to the seller. And it's monotone, non-decreasing. As a concrete example, we can think about just taking the average of the signals. This is just a simple example. Okay. So how does the mechanism look like in this setting, in the interdependent values model? We all know that when the players know the true value, they bid for the value. But here, they don't even know the value. So what do they bid for? They bid for the information that they have, the private signal. And according to the private signal and the public valuation functions, the seller decides upon an outcome and a payment. And in this setting, the best solution concept we have is ex post incentive compatible, meaning that bidding your true value is an ex post Nash equilibrium, which means that if everybody else bids their true value, the true signal, you might as well reveal your true signal. This is the best response for you. Okay. Our goal in this, my goal in this talk is to talk about welfare maximization. And we know that if we're in the private values model where every player knows his value, VCG basically solves the problem, even for the most general domains we can think about, far beyond combinatorial auctions. But in the interdependent value model, even in very strict single parameter environment, we have to have some single crossing type condition, which I described in a few slides, to achieve the optimal allocation. And without it, we have some impossibilities, which I also will describe. We can't achieve the optimal allocation. But we want to talk about even much richer domain of combinatorial auctions with interdependent values. In this setting, unless we have some degenerate cases, we can't achieve the optimal allocation even. We don't have nice conditions like single crossing. So we don't know how to, we can't implement the optimal allocation. And the natural question is, can we approximate welfare? I'm a computer scientist, so a natural question that arises, if we can achieve the optimal allocation, can we approximate it? And we answer it that in a positive way for some under some condition. So if signals have some modularity condition, we can basically get approximation results for combinatorial auctions. So the statement, high-level statement of our main result is that we get the first welfare guarantees in the interdependent values model for combinatorial auction setting when signals exhibit marginal returns, decreasing marginal returns property. Okay. So I'm first going to show you that approximating welfare without any condition, even for a single item, is impossible. I'm going to show you an unbounded gap for deterministic mechanism and an end gap for randomized mechanism. So for the deterministic mechanism, the example is really simple. Let's assume we have the dog doodle from before. A seller sells this dog doodle. And we have two potential buyers, which are me and Kira, my co-author. But the twist here is that only I have the information. Only I know who painted this. Only I can see the signature. So I have the signal, the private signal. And if the private signal says that my son drew this in kindergarten, then Kira doesn't care about this dog doodle. She has a value of 0. I have some sentimental value for it, let's say $100. So if the seller hopes to get any welfare guarantees, he must allocate this to me. But if I have a high signal, if it's a Picasso, then I'm not such a fan. My value increases only to 200. But somebody else, Kira is art enthusiastic and enthusiast, and she has a value of $100,000 for this painting. So again, if the seller wants to get some reasonable bound, he will give this item to Kira. And what you need to know here is that if I know it's a Picasso, I have no reason to give you this information to the seller. Because if I say it's a Picasso, I come home with nothing. Well, if I say it's my son's, I get the painting, and I pay it most my value, which is $100. So I still get a utility of 100. So if I know it's Picasso, in this case, I'd say it's my son's. So any truthful mechanism has to allocate, in both cases, either to me or to Kira, and lose basically an unbounded gap, because we can change the 100K to any number larger than 200, and get that basically deterministic mechanism loses an unbounded gap here. Okay. So just to have you, we saw one allocation that can't be implemented, the optimal one. And to give you some characterization that you can relate to, in this model, similarly to milestone that we know and love in the private values model, an allocation can be implemented if and only if the allocation rule is monotone in the signal, meaning that as an agent increases the signal, his allocation probability also increases. Okay. Here are some examples. For instance, on the middle row, we can see it's not monotone. It's monotone on the left-hand side. In the right-hand side, it's not monotone. Okay. So as I said, a natural question, okay, we saw an example where deterministic mechanism can get no bound. A natural question to ask is, can randomization help? And unfortunately, the answer here is no as well. There is an example, there is an instance, where any random mechanism loses a factor of n compared to the optimal allocation, and which is basically the same as giving just the item to a random bidder, to a uniformly random bidder. So how does the example look like? So we have n agents. Each has a signal which is either 0 or 1, and its value is 1 if and only if all other signals are 1 simultaneously. So it looks something like this. We have a bidder 1, for instance, and he's happy he has a value of 1 if and only if all the signals increase to 1 of other players. And we can show for this valuation that we said already that if we want a truthful mechanism, we have to have a monotone allocation. And we can show for this instance that any monotone allocation loses a factor of n in the approximation ratio compared to the optimal allocation. So basically, we can do anything deterministically or randomly. And yet, this is a widely studied model in economics. And you might as well ask why. And the reason for this is that they bypass this problem by adding a single crossing assumption. So this was done in almost all works in economics and works that we know of in computer science. And it enables us to implement the full efficient mechanisms in simple single parameter domains. And roughly speaking, this single crossing assumption means that an agent cares more about his information, then other agents care about this agent's information. So agent I is more sensitive to his own signal, then other agents are sensitive to I signal. And if you remember the example with me and Kira, this was not the case because as I increased my signal, Kira cared more. So this was not single crossing. So this condition makes sure that we can implement the optimal allocation. But we have two natural problems with this condition. The first one is that there are many realistic and simple examples where single crossing just doesn't hold. You can think about information asymmetry. One has the information, but he's not the one that cares most about the item. And the other more concrete problem is that single crossing is a single parameter condition, and it goes hand in hand with the monotonicity characterization I showed you a slide before. So it doesn't help if we want to go beyond a single item. And in our case, we want to go beyond single item. We want to talk about combinatorial auctions. So combinatorial auctions, in combinatorial auctions, we have m heterogeneous items. And each buyer might have a different value for each subset of items. Okay. So how does this model looks like in the interdependent value setting? So again, each bit of I has a signal Si, which can be either single dimensional, just a single number, or it can have a signal for each subset of items, maybe. And now this agent has a valuation function which is interdependent for each subset of items. So for each subset of item T, he has some valuation function VIT, which depends on all the signals of all the players. As a concrete example again, you can think about maybe unit demand valuations in this case, where an agent only cares about one item. So in this case, for unit demand valuations, we have a valuation function Vij for every item j, which takes all the signals. And its valuation for a subset T is the maximum over this valuation function. You can think about maybe houses if you want a concrete example for single unit demand valuations. Okay. So what are the challenges that we have with the combinatorial auctions? First of all, we don't have nice characterization of truthfulness like we had before. Monotonicity doesn't make sense in multidimensional environment. We have some conditions, but they are very complicated to work with, and they don't help us much. And because of that, single crossing doesn't help us as well. I already said it goes hand in hand with monotonicity. So if we don't have monotonicity, single crossing doesn't help us. And even worse is that there are mostly what's known is the impossibility results. That basically says that unless we have a very degenerate case, we can't implement the optimal allocation. Okay. So how do we tackle this problem, this impossibility? To give you the notion of our solution, let's recall the randomized lower bound. The bidder had a value 1 if and only if all the signals were 1 together, which means that the signals were highly complementary. Only if all of them were high together, the bidder had a value of 1. So our approach will be to consider a case where signals act more like substitutes. And we formalize it by saying that signals have decreasing marginal returns. So formally, we call this notion submodularity over signals, SOS. And we say that valuation function is submodular over signals if when all signals but j are lower, the signal of bidder j is more impactful. We're not more sensitive to signal of j. To see it in an example, let's go back to the Picasso example. So if everybody thinks it's just a kid's doodle, and I reveal it's a Picasso, the effect is much more dramatic than if everybody already thinks it's a Picasso, and then I reveal it's a Picasso. And in math, it says that if S minus J is lower, all the signals but J is lower on the left-hand side, the change in the signal of bidder J changes the valuation more than if the signals are higher on the right-hand side. So if the signals but J are lower, signal J is more important. Okay. And we can extend this definition to combinatorial auctions if we say that a valuation function is submodular if every VIT for every T is submodular. So this is a nice definition for another reason that almost all the examples we know in the literature satisfy this. But even if we don't satisfy this exactly, if we don't have this property exactly, but with a D on the left-hand side, which is a much richer domain, we can still have some relaxed approximation guarantees. Okay, so what are our results? I'm going to talk about our results for single item, for downward close constraint, meaning that each bidder has a value, but the set of bidders that can be allocated together is downward close, and for combinatorial auctions. So what was known before is that for single item, we can solve the problem under single crossing, and we gave square root n approximation if we have relaxed single crossing condition in the last EC. For down close under down close constraint, single crossing doesn't help us. We can't achieve the optimal. We can't achieve any deterministic nice guarantee. And for combinatorial auctions, I already said that we have impossibilities. We don't have anything positive, basically. And we get 4 approximation for the entire domain for all the cases. Well, in the last case, we also need some separability condition on the valuation that I'll describe in a couple of slides. So these are results for welfare, but we also have a result for a revenue maximization for a single item. Well, all previous results needed a single crossing type assumption. And we get a constant approximation without single crossing. And we can also have the results with a relaxed notion. We lose a factor of roughly d for welfare and d squared for revenue. Okay. So let me, to give you a taste of the techniques, let's focus on the simplest case of one item. And let me give you the entire mechanism. It's pretty simple. So the mechanism for a single item looks like this. The first step would be just to split the bidders uniformly at random to 2 sets A and B. So we flip a coin for each one to see if it's in A and B. The second step will be for each bidder in B to take to assign a weight to him, which is his value with his signal, the signals of bidders in A, and all the other signals zeroed out. And so we do it for every signal in B. The signals for every bidder in B. The bidders in A can't win this auction. And we just allocate to the bidder in set B with the highest weight. So it's pretty simple. It's a random sampling type auction. And I'm going to show it's truthful. And to show it's truthful in single parameter setting, I only need to show it's monotone. The allocation rule is monotone. So let's fix an AB partition. If we show it's a monotone over all partitions, then it's monotone in random or in expectation. So let's fix an AB partition and look at 2 cases. The first one is that the bidder is in set A. In this case, no matter what he reports, he doesn't win. So it's trivially monotone. The other case, where the bidder is in set B, if he increases his signal, he increases his weight and doesn't affect all the weights of other bidders in B. So you can only become from a non-winner to a winner. You can only pass the threshold of the highest one. So it's monotone. Therefore, it's truthful. So truthfulness was easy. To give you the approximation, let's look at I star, which is the bidder with the highest value overall, the true highest value. This bidder is in set B with probability half, because we do it randomly. And I'm going to claim that given that this bidder is in set B, his expected weight, his expected value with his signal and the signals of A, is at least half of its value. So the winner has to have a larger weight. So with probability half, we get an expectation half of the value of the highest one, which gives you a factor of 4 approximation. So we're going to prove this claim. So if we have a bidder I, and we take his signal and split all the other bidders to 2 random signal, sets A and B, and we take the signals of A and zero out the signal of B, I want to claim this gives you half of the value of his real, half of his real value with all the signals. So this is what we want to claim. And we can extend this claim to get a d+1 factor for d submodular functions. Okay. So again, what we want to claim is up above. We want to say that it is value with half of the random half of the bidder is half of the value. So let's look at 2 events. The first one is that we take some set, random set C is set A, and we take their signal, and zero out the signals of set D of bidders. In this case, we get the value on the right-hand side, VI with this signal and the signals of C. The other case is that they swap roles. Now, set D of bidders is set, we take their signals, they act as set A, And set C of signals act as set B. We don't take the signals. In this case, we get the value of the bidder with his signals and the signals of set D. And we want to claim that if we add these two together, we get at least the real value. And this basically ends the proof, because if we have this claim, then we just can couple this event in the expectation and lose it, because they both happen with the same probability, we lose a factor of half. Okay, so let's prove this claim, and let's take the second term. Let's start with this one. So if we take the second term and subtract something positive from it, we get something smaller. So let's subtract the value of the player with only his signal. And now this is larger by some modularity than from the difference if we take the signals of C. So if we take the signals of set C and have the same difference, then we can use the modularity to see this. The effect is smaller than if we zero out the signal of C. This is basically just a corollary of similarity. And now we're basically done, because on the left-hand term is just the real value. And the right-hand term is just the value in event 1. So we can move sides and get what we want to prove. So it's pretty simple proof. Okay. So again, to connect to the mechanism, we said that the highest bidder is in set B with probability half. And I just showed you that in this case, we get his weight is in expectation half of his value. Right. And we want to extend the argument to combinatorial auctions. And to do that, we need some separability assumption, which means that we can separate the effect of the signal of player I from the signals of other players. If we have a valuation VIT of set T, we have a function that takes the signal of of player I, and a function that takes all the other signals. And we can separate these two. And fortunately enough, still this condition holds in almost all examples in the literature. So this separability assumption is pretty natural. And using the separability, so to extend this mechanism to combinatorial auctions, we can still use some random sampling type techniques. And approximation follows pretty easily. But the problem here is truthfulness. Truthfulness is not immediate because it's a multi-parameter setting. So we need to come up with payments to show it's truthful. But in the case of separable valuation, we can give you VCG-inspired payments to get truthfulness. Okay. So to repeat what I talked about, I described why similarity is so useful, because it allowed us to have the first positive results for the domain that we had negative results mostly for, which is combinatorial auctions with interdependent values. And I want to encourage you to think about, now that we can talk about combinatorial auctions, maybe we can talk about other interesting problems that we had in the private value model of revenue maximization or complexity questions. And think about this in this new model. I think it's a reasonable direction. Okay, so thank you.
We have time for a few questions. Matt?
Do you know whether or not it's possible to get similar guarantees with something deterministic?
So let me repeat the question. It was, do you know whether it's possible to get similar guarantees with something deterministic?
So the problem is that the example of me and Kira was SOS modular, and we had an infinite bound. We have to have, this is a good question, but we have to have randomization.
Kostas?
Anonymous?
So if every reader's valuation is symmetric with respect to permuting the signals of the other guys, can we get a factor of 2 or better?
So the question was, if every bidder's valuation is symmetric with respect to permuting the signals of the other guys, can you get a factor of 2 or better?
Yeah, I guess we can improve the factor because we don't have to catch a significant guy in the sampling. It's like we can somehow get a better sense of what's going on from the sampling set. We don't have to catch the big fish in the sea. I think we can improve it. We didn't think about it.
Vince?
Is there a natural way to implement these auctions without the recognition
So the question was if there's a natural way to implement these auctions without directly reporting signals, but rather asking about valuations or something.
So I think a related question is what happens if valuations are private as well, maybe. Here, in our cases, I don't know if. And there are some works, but it's a good question how to, I think, extend to the case where, like, if you know your valuation function, but you don't know your real value, you can think about makes sense. And it's a good question to extend the results, but we don't have yet.
I had a question. So in Sheng Wu's behavioral economics tutorial yesterday, he talked about cursed equilibrium, which I kind of missed the definition, but it has something to do with interdependent value settings. So, you know, it's like people misinterpret the actions of others as a function of their type. So it's an Bayesian world. And I was wondering if you thought about maybe like, you know, getting some kind of approximation results under behavioral assumptions about the agent's actions.
No, we haven't. But it's a good question. I don't know.
Okay, if there are no more questions, before we congratulate all the authors again, I want to mention that as part of FCRC, Ramesh and I were able to nominate some of the plenary speakers for FCRC, and today's plenary speaker is the one that we nominated, that one, it's Cynthia Dwork, so I highly encourage you to attend her talk. She's talking about differential privacy in the US Census, so I think it's very related to the types of things this community thinks about, you know, like data markets and the importance of data. So that is going to be wherever the plenaries are held for FCRC in 20 minutes. And then let's thank again the speakers of this session.